So now, coming up, I would like to introduce Štěpán Balážik. Almost got it right. I've been practicing the name all day, by the way. They are going to talk about how they created a tooling framework for independently evaluating resolver cache maintenance policies, and we'll be sharing some of their results. And I'm actually really, really looking forward to this one because I think it's an important and interesting topic.
Good afternoon. Just a word, organizational word. The workshop for pronunciation of my surname will be collocated with Shannon, so see you there. And yeah, what I'm going to talk about is caching and DNS resolvers. And I don't have to tell this group that caching is crucial for DNS resolver performance. And Kathy already told you that LRU, or least recently used cache policy, is ubiquitous in resolvers nowadays. And my question, which I'm not going to answer today, sorry, is can we do better? And the questions which I'm probably gonna, or hopefully gonna answer today, wearing my QA hat on. Oh, I forgot to say, I work for ISC on Bind. Which I'm going to answer are what does better mean and how do we test it? So, quick note on agenda, I will quickly talk about caching in DNS and caching policies, and then I will tell you about my policy evaluation toolchain called cache test. Well, that sounds good. And I will give you a glimpse of results, really an appetizer, because there's not much to write home about yet. So what is a cache policy? It's a set of rules that that answers these two questions. What records to put in your cache and what record to throw out, or fancy word to say that is evict when the cache is full. And the least recently used policy stores all of them in the cache and evicts the one that has been least recently used. It's so simple. So what is a good policy? So the literature on DNS caching policies is sparse, but the rule of thumb that the literature gives you is it's LRU, or least recently used, with some tweaks. But you usually want to do is to minimize cache misses. There was an interesting discussion yesterday talking about whether we should care about server selection in DNS resolvers. If your caching policy is good, you don't have to care that much because you will have all the cache hits and no cache misses, right? But in DNS, cache misses are not created equal, or at least in recursive resolvers. So they depend, the cost of each cache miss depends hugely on what's currently in your cache. So in this example, we have glue and NS records for a zone, so we can, when the client query comes, we can directly ask the authoritative name server, and we get the concrete answer with a cost of 1 without DNSSEC. If the cache is empty, the cost is obviously larger, the cost is free. But everyone or anyone who ever debugged a DNS resolver knows that the costs grow much, much bigger. So I have talked about cost, and I will tell you how I evaluate the policies. So I take the number of needed queries for each client query as a good indicator of the latency that the client observes. I am working kind of high level on records and DNS types rather than bits and bytes. Also, but I don't care so far, or for now, I don't care how the records are stored in memory and how they are laid out. I don't care about it so far because I'm working outside of a real resolver. This is because, well, resolvers are a beast to work on. If you ever worked on one, you know that. So I'm trying to, well, find some candidate caching policies which we can later implement in bind or, yeah. The third thing is that I'm working outside of the internet, which is ever changing. So I am building a model which allows me to do everything in a reproducible manner, but I'm starting with real client data, so real client traffic that some resolver somehow got. So next I'll talk about the cache test toolchain. The first step in the toolchain is to take the client queries from a PCAP and get only the unique requests or unique queries. Then I collect all the relevant authoritative data. Then I use them to build the simulation environment. And in the fourth step, it all comes together. I take the policy implementation or the policy rules, the PCAP, the queries themselves, and the simulation environment, and I calculate the costs for all of the queries in the PCAP in order. So the first step is quite simple. I have PCAP, and with DNS-JIT and some shell scripting, I get a list of unique name type pairs, which I resolve. I resolve them. I resolve them using not resolver with a custom module, because not resolver, due to its architecture, it makes it easy to stand between. So my module for not resolver stands between the iterator and the cache and listens on everything that's going on and notes all the important authoritative data. The important authoritative data is mostly TTLs, NS sets, and some other stuff. This is all put into SQLite database to then parsed in the next step. Currently, I'm not storing any RR6 TTL, which should be, I think, the same as the TTLs for the concrete data. I'm not working well with NSEC aggressive caching, which is hard, as we heard today. And this is real internet, so there is serve fails and retries, so really the data collection isn't perfect, and it never will be. The first step is to parse the authoritative data, and I use DNS-Python for that. And the main limitation here is that I need the data organized in zones, but the idea of zone from the resolver's point of view is kind of fuzzy, so I have to do some what the statistic buffs call imputation. So I have to basically fall back in about 1% of the zones to some sane values for SOA TTL and for NS sets and other stuff. So, and the fourth step where it all comes together is benchmarking the policies. So first I define what cache policies is in kind of a little bit more detail. I will show you the way I will talk about the way I deterministically calculate the request costs and then simulate the traffic. So this is our good known, least recently used policy. And for me, the policy is really a tuple of two methods. One is put, so when you are putting something in the cache, and one is peek, when you are looking if something is in the cache. This is, I'm sorry for the terrible pseudocode on the slide. I assure you that my actual code is even worse. And yeah, so this is the pseudocode for LRU. I spoke about it earlier. There is the notion of ordering the cache records by the time they have been last accessed. And I got, well, curious, and I remembered what I learned from the literature, and that you should tweak LRU a bit. So this is what I came up with. This is nothing groundbreaking. I'm just using it as an example of another policy. So you mark some of the records as important, and if you can avoid it, you don't throw them out of the cache. So this is just an example of different policy. So for request cost calculation, that as I shown in the example at the start of the talk, that is determined by the current state of the cache, and when the client request is resolved, we get out the cost of the request and also an altered cache state. So the records that are needed to resolve this client request are added to the cache. And the caveat here is for the calculation to be deterministic, we need the server selection to be randomized, which has some implementation, which creates some problems in implementation, but for now, for approximation of the cost, that's okay, I think. And this simulating a traffic is just calculating the cost of each query with the side effect of altering the cache. I know this will break in Python, but this is my pseudocode. This is not Python, so we are okay. The initialization of cache and costs in the pseudocode. And this is also the last piece of pseudocode you will see in the slide, so you're welcome. And quick word about the results. These are mostly illustrative and a starting point to further research. The main point of this presentation was the tooling I presented before. And as I said at the beginning, there is nothing much to write home about really in the results I'm going to present. That being said, this is the data set I worked on is from a telco in Europe. It's normal traffic, so there is no attack going on, and I will circle to that at the end. It's quite old, and I don't know how old because I'm so far in the NDAs that I am not allowed to even know that. And but it's old, and that shows because there is a lot of NX domain answers in it, or whatever we are calling it nowadays with DNS-SEC. And it's only 1 hour, so TTLs of most records don't really expire in that. So this is just an appetizer of what we can do. And the policies I used for these presentations are LRU, which are presented, the important LRU, which I showed before, a policy which is called least frequently used, which what that is you for each record in the cache you keep how many times you accessed it, and once it comes to throwing someone out of the house, you throw out the record which has been least frequently used, as the name suggests. And as a baseline, I'm using an unbounded policy which just doesn't have any limit on how many records it stores. To the best of my knowledge, this is not the policy that is used by Unbound. Unbound uses LRE, just so we are clear. So as I said, in this histogram, it's quite visible that in normal operations, the policies are indistinguishable from themselves. But it's interesting to, I think this graph for more interesting scenarios will be interesting to look at. And another thing that I like to look at when thinking about resolution cost is the tail of the distribution. So how many, what portion of the request is resolved in more than, for example, 10 or 20 queries? And the interesting thing, one of the interesting things you can see is that in normal operation, the important LRU is indistinguishable totally to the single request difference from LRU. What that means is that LRU is pretty good at recognizing which records are important by itself. And yeah, so what my next steps are to optimize my code, because this is the first cut and it's written in Python, and it's slow and the code isn't up yet. It will be as soon as possible. I want to test on more kinds of traffic. So if you have some PCAPs from your resolver you are running at home or at your university or elsewhere, please send them to me. And the, I think, interesting idea to explore is to take this legitimate traffic and to mix it with some synthetic attack traffic and then measure the performance only on the legitimate traffic, not caring about how fast we resolve the synthetic attack or the attack traffics. And I want to also test more policies, because there are more established 4- and 5-letter acronym policies to be tested in literature, and maybe some new ones, domain-specific, pun intended. So if you have any ideas of which records you would like sticking in your cache for longer than others, well, DM me, and that's it. Thank you.
Thank you very much, Štěpán. Do we have any questions?
Thanks a lot. It was a great talk. We enjoyed it. It reminded me of some work that we did a couple of years ago for a different reason, and that is one thing you might have to add to your validation, and that is you see the cache as a singular cache for all clients. There's this thing called ECS that kind of talks about. So adding that is interesting, I can tell you. Might want to think about it.
Thank you.
All right, I'll just hold it. So remote question from Benno from NLNet Labs. Is there a limit to the complexity of the cache policy that you can model? For example, with prefetching of frequently used names, so the cache entry for the name is never expired.
I'm thinking about prefetching. So prefetching is, well, you can do prefetching in this tool, and yeah. So I'm thinking about the complexity in the well, the thoughts about complexity will come in the next step, because someone will have to implement it in bind, and we want bind to be actually fast. And there is consideration of adding more cycles to the happy path, to the path of cache hit, so we don't unnecessarily prolong that. But this is further in the research. This one is to just pick some candidates which would be nice to have, and then crash into reality later.
I have a question.
Yeah.
Do any of your testing policies actually actively take into account the TTL of the content of cache, or is the test too short for that?
Well, the caching policies are pieces of Python code, so you can express whatever you want. And so the things I tested are the four policies I presented. I haven't had time to think about that much.
Puneet Sood from Google Public DNS. I have a couple of points. One is a question and one is a suggestion to try. So one question is, have you tested this in a concurrent resolution environment where there's more than one user query being run at the same time?
No.
So there'll be some concurrency and like locking impact on the more work you do upfront on the read path, it will have an impact. So I'm curious.
Yeah, I'm aware of that.
Yeah.
I am covering my eyes and ears for now about it. This will come in the next step when we are actually thinking about implementing it.
Yeah, I'll look forward to seeing that. The other suggestion I think to see is if you go in the other direction of a simpler algorithm, right? What if you don't even do LRU, you do something which is even simpler? I have thoughts on it, but I would like to see if you have other variants you would want to try.
Well, I'm open to suggestions. If you have some simpler policy in mind, maybe it's so simple you can tell me now.
Sure, meaning basically is just look if it's expired or not, don't even care about LRU, start somewhere random in the cache, assuming it's a linear list, a circular linear list, start somewhere in the middle and pick the expired entry at random, essentially.
Yeah, that sounds interesting.
Okay, thank you.
I have another question. Oh, well, it's a commentary, really. I have a suspicion that you can devise a perfect policy based on there being no implementation considerations, but that when you try to implement the policy, that the implementation of the cache itself may cause the results to be different from the ideal policy. Had you thought about that?
Yes.
And Petr, yes.
Petr Špaček, ISC. I want to say, if you are interested in this topic, please help us and give us some data to test on. Otherwise, we will be testing on, 2 pcaps we have, which are sufficiently long, and that means over-optimizing, overfitting the algorithm for that specific set. So if you want to see next presentation about the algorithm which actually works very well, and you can then copy the algorithm into your implementation, please help us to get the data, because without the data, this will be kind of academic exercise.
I would add to that there are mechanisms for collecting the data in an anonymized fashion that we can let you know about. And also that if you do provide us with your data, we are using it to test Bind's performance by QA. So guess what? We're testing and optimizing performance against your resolver's typical traffic profiles, so it is a good thing. Right, enough of the marketing stuff. Thank you very, very much, Štěpán, for your talk. It's been very interesting.